So what's interesting to observe in this definition that we have now, multiplying two by two matrices together, right? Because that's exactly what we have, right? I have a 2 by 2 matrix times a 2 by 2, and we get another 2 by 2. By the way, we'll soon see that the dimensions don't really have to match in order to define matrix multiplication properly. But in this case, that's what the definition is. If you want a good way to remember how to perform a matrix multiplication between two matrices, to observe that this thing here, that's actually the matrix vector multiplication A11, A12, A21, A22 multiplied by the first vector of the matrix B11, B21. So essentially, to get, for example, this entry here, we multiply the first row of this matrix against the vector. What I mean is we multiply component-wise and we add up the product of the components. And this guy is the same thing. Okay, so to get the second row, essentially we're doing the matrix vector multiplication A with the second column now of B. So it's a good way of remembering how to apply matrix multiplication. So we're going to take a look at a specific example. Example 1, we want to multiply the matrices 1, 2, 3, 4, 5, 6, 7, 8. So in terms of linear transformation, what we're doing, okay, is that we're coming up with a standard matrix of the linear transformation that would actually perform first a linear transformation T1 with this standard matrix, and then perform another linear transformation T2 with standard matrix 1, 2, 3, 4. Okay, so this is in the context of linear transformation. But matrix multiplication actually has applications that are beyond linear transformations, but it's a good way to introduce that concept. Okay, using linear transformation is a good way to introduce this concept of matrix multiplication. So let's try to multiply these together. Maybe first thing is maybe you can want to try this by yourself. So pause and come back and see if you were able to do it. Okay, so to get I'm going to get a 2 by 2 matrix. Now to get the, maybe I'll leave myself a bit more space. To get the first entry, like the entry here, okay, what I need to do is multiply, I want to do, well, essentially to get the whole column here, I'm going to multiply this matrix with the vector 5, 7, okay. Now to do this, to get this entry right here, what I'm going to do is multiply this row against this column, okay, component wise. So 1 times 5 plus 2 times 7. That's my first entry. So maybe let's write it here. 1 times 5 plus 2 times 7. That's going to be 19. Right. And then to get the entry here, I need to multiply this row against this. Need to multiply this row against this column 5, 7. So that's going to give me what? 3 times 5 plus 4 times 7. So that's 15 plus 28. So 43. So that's my, okay, now I want to get this entry here. Okay, so essentially to get the entire column here, I need to multiply this matrix times this column, or this vector. So it's really a matrix vector product that I'm doing to get the second column. So I need to multiply this row against this column to get this entry right here. So that's going to be 1 times 6 plus 2 times 8. So that's going to give us 6 plus 22. And finally, for this guy, I need to multiply this row against this column. So that's 3 times 6 plus 4 times 8. So 32 plus 18, which is 50. And that's my product. Now, okay, we're going to generalize this a little bit, okay? Now, instead of having two linear transformations from R2 to R2, we have something a bit more general, okay? We started with a linear transformation T1, that's from RR to RM, and T2, which is from Rn to RR, okay? So if you take a look at this, I've got T1 that takes me from RR to RM, and then I have one that also takes me from Rn actually to RR, like this. So T2 does that, and T1 does this. So it makes sense to talk about the composition of these two. Oh, actually, I got this wrong since it's going to be T2 that we do first, right? It's the one that goes here. So it's T1.D2. Okay, and T1.D2 will go from Rn to Rm. So you see, this is what we have here. Now, so I'm going to assume that T1 has a standard matrix A, and that T2 has a standard matrix B. Okay, so T1 will be AX and T2 will be BX. Okay, and okay. And if we keep reading, the standard matrix A and B of T1 and T2 are respectively M by... Okay, yeah, so let's talk about the dimensions. It's true. So if we look at A now, okay, so A applies to a vector X, right? So that's A is T1 of X, right? So that's going to be AX. Now X, right, is that same X here. So T1, remember, it takes a vector in RR, so, right? T1 takes a vector in RR. So this is in RR. And the whole thing is going to be eventually in Rm. Okay? So I'm going to have, you know, a vector x1, x2, all the way to xr. Okay? Like that, because x is in RR. But if I want to multiply this by a matrix, you see, I have to have, right, as many columns in A as I have rows in X, right? So these will have to match, right? As I multiply, I need to multiply, you know, every entry in the first row of A, for example, against all the entries in X. So I need to have just as many columns, right? So A here has to have R columns for this matrix vector to work out, okay? But if I want to be in Rn, M at the end, I need to have M rows. So, I mean, I can't write it here, M rows. So A is going to be a matrix that's M by R, you see? M by R. And if I do the same analysis with B, it's going to be R by N. Okay? So AB, okay, is a product where the matrices are not necessarily of the same size. It's M by R, R by N. But for the matrix product to work, actually these have to match. Okay? Just like over here, right? RR is common to both linear transformation T1 and T2. One is the output of T2, the other one is the input of T1. So that's why the middle entries here, the middle indices of the dimensions of A and B, they have to match. So these two have to match for the matrix multiplication to work. And what I will eventually get is a matrix that's M by N. That's because it's taking it's going to be taking a vector in Rn and outputting a vector in Rm. Okay, so let's take a look. All right. So the definition is, it looks complicated. So I think what we're going to do is we're going to skip it for a moment and actually do the example. Okay, so I'll show an example how that works. So let's look at example 2. Okay, so in example 2, okay, let's look at the dimensions. So this is a matrix that A is 2 by 3. And actually I didn't write it, but this is matrix B. B is 3 by 4. So you see how these middle, these dimensions actually match. So that means I'm going to be able to do the matrix multiplication AB. But if I try to do BA, okay, if I try to do BA, see B is going to be 4 times 3, and A is going to be 2 times 3. These actually don't match, so this is not defined. I cannot do this. Okay, this is undefined. If I think in terms of linear transformation, T1, which would be T1 of X, let's say, okay, it would be A times X, okay. Now let's take a look. Like A would be 1, 2, 4, 2, 6, 0, right? And that can only apply to a vector X with 3 components. You see, because as I do the matrix vector multiplication, right, I need to be able to match every entry in the first row of A and in the second row of A2 with entries in X. So X has to have as many rows as A has columns. So this is a vector in R3, okay? And what's the output? Well, as I output this, right, as I multiply, I'm going to multiply the first row of A against X. I'm going to get an entry here. And the first row of A, the second row of A with X, I'm going to get another entry here, okay? So overall, I'm going to get something that's in R2. So you see T1, it takes a vector in R3 and outputs a vector in R2. If I take a look at T2, which is Bx, okay, well, B is what? It has 3 rows, 4 columns. So that means X needs to have 4 rows like this, X4. So B, T2, is going to be taking a vector in R4, and because B has 3 rows, it's going to output a vector that has 3 components, 1, 2, 3. So that's going to be in R3. So it's going to go from R4 to R3. Okay, so you see it makes sense to have T2 composed with T1, because T2, I can take a vector in R4, output something in R3, so that's T2, okay, and then take the vector in T3 and output something in R2, that's T1 that does that, okay. So overall, what I can actually do is the composition, which is T1 dot T2, okay, and it's in its standard matrix will be what? Well, it's going to be A times Bx. So AB is the standard matrix I'm looking for. Okay, so let me erase all this and let's try to calculate and maybe let's talk about the dimension of AB, right? AB is it's taking what? It's taking a vector in R4. Okay, so X is in R4 here, right? This X is in R4, right? So it needs to have four columns, and it's outputting something in R2, so it's going to have 2 rows, so it's going to be 2 by 4. Let's take a look. You see, if I can do A times B, that's going to give me a matrix that's 2 by 4. You see the outer indices? That will give me the dimension of my matrix AB. Okay, so we can, I don't know where you want to write this. I'm going to erase it because I need more space to complete the example. Okay, but you should definitely keep this. Maybe you can write what follows somewhere else on this sheet of paper that I hope you printed. Okay, so we're going to multiply these two matrices together, 2, 6, 0, against this. 1, 2, 7, 5, 2. Okay, so that's AB is equal. Okay, now I'm going to end up, okay, it's easy to figure out what the size of the resulting matrix is going to be like. So I said that A is what, 2 by 3. This is 3 by 4. So we're going to end up with a matrix that's 2 by 4. So 2 rows, but 4 columns. Okay. And the way this works is very simple again. Okay. So the best way to, I guess, perform your matrix multiplication is to do many matrix vector multiplications. So we're going to first start by multiplying the matrix A with the first column of B. So if I do this, okay, let me figure out this entry here. I need to do what? 1 times, so this row against this column. So 1 times 4 plus 2 times 0 plus 4 times 2. So 1 times 4 is 4, 2 times 0 is 0, 4 times 2 is 16. So I'm going to be getting 20 here. Okay. And then after that, I multiply the second row of A with the first column of B. So 2 times 4 plus 6 times 0 plus 0 times 2, that's 8. And now I have the first column. Okay. So afterwards, I want to multiply A with the second column of B. And I repeat this. Okay. So this entry here is what? This is going to be 1 times 1 plus 2 times minus 1 plus 4 times 7. So that's 28 minus 2, that's 26, plus 1, 27. Okay? And this guy here, that's the second row of A multiplied by the second column of B. So that's 2 times 1 plus 6 times minus 1 plus 0 times 7. So that's minus 6 plus 2 minus 4. And you do that for the third and fourth and the fourth column of your product. So if I do this, we get those values. So try to see if you can come up with those two columns by yourself. Okay, so that's it. That's how you multiply matrices together. And we see that they don't have to have the same size, really. Okay, so before, since we had matrices in R2 from R2 that were linear transformations from R2 to R2, matrices related to those linear transformations, it worked, right? They gave us the product worked because the inner dimensions work, and we got a matrix that was also 2 by 2 because the outer dimensions were 2 and 2. But it doesn't have to be this way. Okay. So, in other words, if you go back and look at our definition here, if A is M by R and B is R by N, let's take a look at the resulting matrix. Actually, let's write it here. If A is M by N, and I multiply this by B, which is R by N, you see the inner dimensions match. So I'm going to get a matrix that's M by N, and that's the matrix AB. So this explains the definition you see there. Maybe the definition you can read it. Okay, it looks like a complicated formula, but this is essentially what I've applied in the example. Maybe what's more important is just to take a look at a specific formula. So if I want AB 1, 3, the entry only 1, 3. Actually, let's take a look at the same time at example 2. If I want entry 1, 3, 1, 3, where's that? First row, third column. So it's this entry. See, that's 1, 3. What do I need to multiply? I need to multiply the no, sorry, 1, 3. My bad. It's not this entry. I want it. 1, 3 is here. This is this one. This is AB I'm looking at. Okay, so if I want just AB 1, 3, only that entry. Okay, what I need to multiply is the second row of A against the third column of B. And this is what you see here. You see these entries here? Those are the entries in the... Oh, I want 1, 3, sorry. 1, 3 is in the first row. It's this one. My bad. Okay, this here. Okay, so first row of A against third row of B. And what you see here are entries in the first row of A. And what you see up here are entries of the third row of B. And as you multiply them, add them up, you can write it using the sigma notation. This maybe saw in calculus, not important. Okay, if that's too far back, you don't remember, don't worry about this. Okay, but that explains essentially the definition. So this big expression that you see here that looks complicated, this is just a general case of this. Okay, for any ij here, that's where I is a row of your matrix A, and is the row of matrix AB, and J is the column of matrix AB. So Ij is the entry in row I, column J. And to obtain this, you multiply the entries in row I of A with the entries in row J of B. Okay, but what's more important is just to be able to apply it in an example like number 2. So we're going to end up with another problem that maybe you can try to do by yourself. You want to find a standard matrix of a linear transformation which performs a reflection across the line y equals x, followed by a reflection across the x-axis. So let's just read that first sentence and try to come up with the answer for that, and then we'll read the second sentence afterwards. So find the standard matrix of a linear transformation which performs a reflection across the line y equals x. So maybe that's the first thing you want to figure out. Okay, we're going to do this with a matrix, using a matrix multiplication. We're going to find the standard matrices of each linear transformation, multiply them together to get the composition of both, right? Because we've got a composition here of two linear transformation. We do reflection and then we reflect again. So maybe we want to find the standard matrix of reflection across y equals x. Okay, so maybe I want to find what that matrix A is. So here we're mapping from, it's not mentioned, we're mapping from R2 to R2. Okay, so we're going to have a 2 by 2 matrix. Now, before you start doing this, I'll remind you, in order to figure out what the columns of that matrix are, the columns are very easy to find. You just need to find where I is sent, okay, and where J is sent. So I and T of J. So maybe draw this. This is the XY plane, or R2, right? We're in R2, and draw the line y equals x. Okay. Draw a vector I like this. Try to see where, if you reflect that vector or that point, right, if you're across the line y equals x, where is it sent? Okay, and that should be the first column of A. And then do the same with J, and try to figure out where that point is sent, and that's your second column. So pause and come back. So I, essentially, if you reflect, is sent onto J. So this is what A is, and J, well, it's sent onto I. So that's very easy to get the standard matrix, and then for that linear transformation, and then let's take a look at the other transformation, the reflection across the x-axis. So actually this one we've seen before. Okay, so if you reflect I across the x-axis, well, it stays where it is. If you reflect J across the x-axis, oh, it goes to minus J. So that's AB. Now, what do we want to do? Do we want to calculate A times B or B times A? Because we want to, what do we want to do first? We want to find the standard matrix of the linear transformation which performs a reflection across the line. So reflect across the line y equals x first. We actually perform A first onto x. And after that, we perform B. So actually here we want to calculate, according to my notation, BA. So the matrix is going to be BA. So we're going to have to multiply B with A to get that standard matrix. Try to do that. So you should get that matrix here. This is a 1 minus 0, 1 minus 1, 0. And if you read the last sentence in the, it says, by comparing this matrix, so the one we just got, to that of a rotation matrix, show that this is equivalent to a clockwise rotation of 90 degrees. And then they remind us what a rotation matrix is. If we rotate clockwise, well, all you have to do is look at, what's a rotation of 90 degrees? Well, let's replace theta by 90 and evaluate this. And now 90 degrees, we're here, right, on the trig circle. So the cosine is 0, sine is 1. So it's very easy. So cosine is 0, sine is 1. And hey, yes, it's the same matrix. Okay, so we get the same matrix. So it is the same thing. So these two reflections actually can be replaced by a single rotation.